Welcome to the investigation into the generative code. We are surrounded by vast datasets, universes of information, and within these universes, some patterns are so incredibly complex and convoluted that they masquerade as pure randomness. Take a moment to look at the visual representation on the screen, the intricate spiral formed by countless individual data points. While it might seem chaotic, this structure is governed by a precise, hidden generative process. It follows an exact, albeit invisible, logic. Our mission today is paramount. We are detectives of data, and we are determined to crack this code. Our task involves much more than mere observation. We need to achieve a profound understanding of the underlying blueprint, the set of rules that governs the creation of every single data point. And once we have achieved this deep understanding, our ultimate goal is not just intellectual victory, but practical application. We must replicate this generative process. We need to construct a mechanism that can produce new, authentic data samples that are indistinguishable from the original evidence. This journey into reverse engineering nature's data patterns is what drives the field of normalizing flows. Let's formalize the challenge and open the case file, an unknown distribution. On the left, we have our primary piece of evidence. This scattered, swirling dataset represents a collection of observations drawn from a specific, complex, and currently unknown probability distribution, which we denote mathematically as P sub x of x. This distribution, P sub x of x, is the hidden source code we are trying to find. Our traditional methods in statistics are excellent at describing distributions, measuring their mean, variance, and shape. But that is not enough here. Our ultimate goal is far more ambitious, and it's illustrated on the right. The goal is to generate new evidence. We need to construct a sophisticated generator that is capable of producing entirely novel data samples. Crucially, these new samples must be so authentic and so faithful to the mechanics of the original data that they are utterly indistinguishable from the evidence we started with. This means we must master the underlying mechanics of P sub x of x. To solve this case, we adopt a Prime Directive, normalize the evidence. The strategy employed by Normalizing Flows is ingenious because it bypasses the need to model the complexity of the data distribution directly. Instead, we choose to transform it. Our goal is to design an elegant mathematical tool, an invertible function which we call f. This function f acts as a translator, mapping the highly complex data distribution x, which is our evidence, into a dramatically simpler, known, and analytically manageable distribution z. We typically choose z to be something familiar, such as a standard Gaussian distribution, a perfect, unstructured sphere of noise. The critical element of this entire approach is that f must be invertible. Because f can be reversed, its inverse function, which we call g, becomes our ultimate generator. We can sample an easy, random point z from the simple Gaussian space, and then map that point back through G into the complex data space, thereby generating a brand new, authentic data point X. This invertible function f is our cipher that reveals the structure, and its inverse, G, is our powerful generative engine. This transformation, while conceptually simple, is bound by a rigorous mathematical principle, the immutable law of transformation. When we move data from one probability space to another, we cannot just ignore the distortion that occurs. The densities must be accounted for. Any transformation between probability distributions is governed by the change of variables equation, which provides an exact formula for calculating the data's probability density P sub x of x. This equation is fundamental to our success. Look at the formula. The density of our complex data at a specific point x is equal to the density of its transformed counterpart, z equals f of x, in the simple world. But this simple density must be adjusted by a critical scaling factor, the absolute value of the Jacobian determinant, denoted as the magnitude of det j sub f of x. This determinant is the key element, as it precisely measures how the transformation function f locally stretches or compresses the space around the data point. If we stretch the space, the density decreases. If we compress it, the density increases. We must account for this stretch and compression perfectly. Here is where our investigation hits a severe roadblock, a challenge so profound that we initially dubbed it the Unbreakable Code. The mathematical law governing probability transformations, which is essential for our exact likelihood modeling, now introduces two critical, seemingly insurmountable obstacles. The first is the staggering computational cost. To successfully train our generative model using the change of variables formula, we must compute the Jacobian determinant of our transformation function, f, if we use a general-purpose, high-dimensional function like a standard deep neural network to perform this complex mapping. The computational complexity of calculating this determinant explodes. It scales with the cube of the input dimension, O of n cubed. For example, if we are dealing with a relatively small image of 1024 pixels, n is 1024, and the resulting computation becomes computationally impossible, turning every training step into a nightmare. The second obstacle is the invertibility problem itself. Remember, our generator relies on having a computable inverse function. G-standard deep neural networks are inherently non-invertible by design. A mapping f is utterly useless to us as a generative model if we cannot efficiently compute its inverse. These twin obstacles mean that the law which grants us the power to model the data perfectly also presents an architecture constraint that renders standard deep learning networks useless for this task. The case seems unsolvable unless we find a completely new approach. The solution to the seemingly unbreakable code did not come from a mathematical breakthrough, but from an architectural insight, what we call the informant, a new architecture. The critical realization was that we don't need to break the immutable laws of transformation. We simply need to constrain our model design so that the laws work in our favor. This is the core principle behind the RealNVP architecture, standing for real-valued non-volume preserving, which is a foundational type of normalizing flow model. The paradigm shift is this. Instead of using an arbitrary, complex function f, what if we impose specific, rigid constraints on the architecture of our neural network? Our goal becomes the construction of a network that is, by its very design, guaranteed to be easily invertible, and, simultaneously, guaranteed to have a Jacobian determinant that is computationally trivial to calculate. By sacrificing some architectural freedom, we gain mathematical certainty and computational tractability, thus solving the O of n cubed complexity problem entirely. The core building block of the RealNVP architecture is called the affine coupling layer, and this mechanism is the centerpiece of our blueprint. The key strategy employed by this layer is simple but revolutionary. Input dimensions are strictly partitioned. Let's take our input data vector x and split it into two distinct halves. X sub a and x sub b the first half, x sub a, is the privileged half. It remains completely unchanged and becomes z sub a. This is a crucial design choice. The second half, x sub b, is the part that undergoes transformation to become z sub b. This transformation is a straightforward scale and translate operation. However, the true brilliance lies in how the scaling factor, s, and the translation factor, t, are derived. These parameters are the output of a separate, complex neural network that critically only takes the unchanged part, x sub a, as its input. This dependency structure, where one part of the data is transformed based solely on the other, unmodified part, is what forces the entire Jacobian matrix into the desired computationally friendly form. This is the critical moment where we expose the villain's weakness. The specific architectural choice of the affine coupling layer, where we partition the data and only transform one half based on the other unmodified half, forces the overall Jacobian matrix into a highly specialized, simple structure. This structure is the key to solving our computational nightmare. Let's examine the matrix structure shown here. The top left block, representing the partial derivatives of z sub a with respect to x sub a, is a simple identity matrix, denoted as I, because z sub a is exactly equal to x sub a, the top right block. The derivatives of z sub a with respect to x sub b is entirely zero, because the component does not depend on the b component. Now, look at the bottom right, the derivatives of z sub b with respect to x sub b, because the transformation of x sub b is element-wise, controlled only by the parameters s and t derived from x sub a, this block becomes a simple diagonal matrix. All of this structure ensures that all entries above the main diagonal of the full Jacobian matrix are zero, resulting in a perfectly lower triangular matrix. This structure is the key to our success. The geometric constraint we imposed on the neural network has finally paid off, and the code is broken. By forcing the Jacobian into a triangular form, we simultaneously solve both of our major obstacles, the determinant calculation and the invertibility problem. Let's look at the determinant first. A fundamental and powerful property of any triangular matrix, whether upper or lower triangular, is that its determinant is simply the product of its diagonal elements. What was previously an O of n cubed nightmare, requiring massive computational resources for matrix factorization, is now reduced to a simple product of the exponential terms on the diagonal, requiring only O of n calculations. It is computationally trivial. On the right, we address invertibility. Because the forward transformation is an affine operation, it is easily reversible through simple algebra. To recover the original data point x sub b, we simply undo the translation and then undo the scaling, using the inverse exponential scale, which results in the formula shown. The key here is that the parameters s and t are derived only from z sub a, which is equal to x sub a. This means the inverse is algebraically simple and incredibly fast to compute. The two greatest obstacles of generative modeling are solved in a single stroke. A single coupling layer, while solving the determinant and invertibility problems, only transforms half of the input dimensions, leaving the other half completely unmodified. To build a truly expressive and powerful generative model that can capture the complexity of real-world data, we must utilize the full operation. Stacking the blueprint, we compose multiple coupling layers sequentially. The critical mechanism between layers is the reversal of the mask. In coupling layer 1, the red block is active and transformed, while the gray block is masked and unchanged. When we move to coupling layer 2, we deliberately reverse the mask. The data that was previously inactive and unmodified is now actively transformed. Importantly, this new transformation is based on the data that was just updated in the previous layer. By repeatedly stacking these simple, invertible layers, each with a reversed mask, we create a single, deep, and highly powerful invertible function overall. The composition of these functions maintains the crucial property of easy computability. Furthermore, the total log determinant of the entire deep network is simply the sum of the log determinants of each individual coupling layer, making the overall training process highly efficient and fully tractable. The training phase is essentially the interrogation, learning from the evidence. Our entire training process is driven by one singular objective: maximizing the log likelihood of the observed data. This is mathematically equivalent to minimizing the negative log likelihood loss function shown here. The loss function, loss equals negative log p sub x of x, breaks down into two vital components that the network must balance: the log likelihood of the latent representation z under the simple Gaussian distribution, and the sum of the log determinants from all the layers. For every single data point x, we push it forward through the deep RealNVP model to obtain its corresponding latent representation z and the cumulative log determinant. The network learns via backpropagation, constantly adjusting its weights to achieve the lowest possible loss. This loss tells the network two things. First, how unlikely the resulting latent variable z is under our target Gaussian distribution p sub z, and second, the scaling penalty incurred by the transformation itself. By minimizing this loss, the network is forced to learn a transformation f that produces latent representations z that are highly likely, meaning they look perfectly Gaussian, while also ensuring that the transformation itself is mathematically sound and accounts for all local stretching and compression. The mission is accomplished, and the files are officially marked case closed, the evidence normalized. After a successful training period driven by the log likelihood objective, the RealNVP model has learned the precise, highly nonlinear transformation required. On the left, we see the original, highly structured evidence, x, characterized by its intricate spiral shape. Following the learned transformation function, f, we observe the result on the right. The normalized latent space, z, the complex, highly organized structure of the original data, has been successfully unfolded and mapped into a simple, homogeneous cloud that perfectly conforms to an unstructured Gaussian distribution. There is no lingering pattern, no spiral, just pure, simple noise. This visual contrast is proof that the network has internalized the generative process. It has not merely described the data, but it has mathematically mastered the mechanism that creates it. The code is understood, and the generative blueprint is ours. Now we reach the payoff, the generator. With the invertible transformation function f mastered, we now pivot to operating in reverse, utilizing our inverse function. This is the generative step. The process is incredibly straightforward and efficient. We begin by sampling random points directly from the known, simple Gaussian base space, p sub z of z. These points are simple, unstructured noise. We then pass these random noise samples through our inverse network, G, which we built using the stacked coupling layers. The model acts as a powerful folding machine. It takes the simple, unstructured noise and accurately folds it back, imposing the complex, non-linear structure of the original data distribution. The result is the generated evidence, x sub nu. Crucially, these are entirely new data points that were never seen during the training phase. Because the transformation G is the exact inverse of f, these generated samples are guaranteed to be true to the original distribution, possessing the same inherent structure and complexity as the initial evidence. We have successfully cracked the code and built the replicator. While RealNVP represented a fundamental breakthrough in tractably modeling complex distributions, the concept of normalizing flows rapidly led to a new underworld of possibility, pushing the methods even further into the mathematical and architectural stratosphere. Two key subsequent innovations stand out. First, GLOW, which built upon RealNVP by replacing the simple, hard-coded mask reversal with invertible one-by-one convolutions. In RealNVP, we manually swapped which half was transformed. GLOW learned the optimal way to permute and mix information between layers at every step. This innovation allows the model to learn far more expressive and powerful transformations, moving beyond simple affine scaling and translation to achieve global mixing of features. Second, we have FFJORD, an even deeper reimagining of the core process. FFJORD views the stack of discrete coupling layers not as separate steps, but as a single, smooth, continuous time process. This transformation is defined by an ordinary differential equation, or ODE, solved by a neural network. This shift provides a much more elegant and mathematically powerful formulation. It removes the necessity of summing the log determinants, replacing it with a single, integral calculation called the trace of the Jacobian, which can be approximated without calculating the full O of n-cubed determinant. These advancements continue to refine and empower the generative code. We have arrived at the final dossier, summarizing our findings on the generative code and normalizing flows. We have established that normalizing flows provide a robust and rigorous methodology for exact likelihood modeling. The entire concept hinges on transforming an inscrutable, complex data distribution, represented here as x, into a mathematically manageable and simple distribution, z, and then utilizing the inverse process for generation. The crucial technical achievement lies in solving the core computational challenge, the intractable O of n-cubed Jacobian determinant. This challenge is overcome not by ignoring the mathematics, but through incredibly clever architectural constraints, specifically the coupling layers of RealNVP, which guarantee both instantaneous invertibility and computational tractability of the determinant. This strategy represents the defining principle of this generative code, a crucial trade-off where we consciously sacrifice some architectural freedom and flexibility in our network design in exchange for absolute mathematical certainty regarding the likelihood and the guaranteed computability of the inverse. The net result of this approach is a powerful class of generative models capable of high-fidelity data generation, possessing the unique ability to both understand and generate data with mathematically precise control.